Sorry for the delay. Come back the same topic. So here, just a minute. My voice is clear, na?
Yes, sir.
Okay. So there are two bands in a semiconductor material, valence band and conduction band. So now we talk about the valence band. The valence band is nothing but it consists of number of electron as per the atomic number. The number of electrons distribute in a outermost cell, right? So 2, then 4, then 8, then 32. Then similarly, so we represent the as per the atomic number, we represent the how many electrons present in a valence band, and this valence band, in that band the covalent bond is present, right? Covalent bond, you know that covalent bond is nothing but the sharing the neighboring electrons and form the crystal, and now we know that valence band. So the valence band, the very important line and always important for exam point of view, the highest occupied energy band is nothing but the valence band. So maximum energy present in this valence band called as a valence band, and the most electron remains bound to the atom in this band, right? So most electron, that means number of electrons present in a valence band. So now there is no any other charge particle present in a valence band. So now then we talk about the conduction band, right? So there are two band, and you know that the conduction band is nothing but the number of electrons available in conduction band we call as a free electrons. But here the electron present in a valence band we don't call as a free electrons, we call as a electrons that sharing with the neighboring electrons and form the covalent bond. So now then the electrons available in conduction band is free to move, right? So is always free for movement. कंडक्शन बँड मध्ये काय असतात ते फ्री असतात मुवमेंट करण्यासाठी. सो दी कंडक्टर वाय दी कंडक्टर इज गुड इलेक्ट्रिसिटी बिकॉज ऑफ they already there are number of electrons present in a conduction band, right? But here in a semiconductor material there is no any electron present in a conduction band. ह्या बँड मध्ये कंडक्शन बँड मध्ये एकही इलेक्ट्रॉन नसतो सेमीकंडक्टर मटेरियल मध्ये. सो ऑल ऑफ यू क्लियर? अँड द एनर्जी इज ऑलवेज present from the nucleus. This part, the bottom part is nothing but the nucleus, and the energy always increasing and is far. Suppose your valence band is near to the nucleus. That's why the highest energy present in a valence band as compared to conduction band. So conduction band is the band of orbital that are high in energy and are generally empty, right? High in energy, right? So high in energy and that is empty. So it is the band that accept the electrons from the valence band. This is very important. The conduction band always accept the electrons from valence band. So what exactly, suppose if you apply the energy at that time, the electrons breaking their bond present in a valence band and move to the conduction band, right? Free for movement. So this is the general diagram of material. There are two layer. Red color is always mentioned by conduction band, and the blue color always mentioned by valence band. And the gap between these two material, sorry, that two band we call it the energy gap, right? Energy gap, and this energy gap calculated or represented by the Fermi level. And you know that you already studied in a Fermi level in a first year syllabus. So leap required for electrons from the valence band to enter into conductor. Leap is nothing but the external energy or external power supply, right? So this is very simple example. You try to understand the semiconductor material, right? So semiconductor material, the valence band present in this area, then the conduction band present in a other road, right? So this the black portion road is we call it the valence band. Okay, there are number of electrons present in a valence band, but only one electrons or very less value of electron present in conduction band, right? And now what is exactly the energy? This middle area we call as a divider, we call as a energy gap, the gap, band gap. And this is a very simple way to understand the actual phenomena of the conduction of current in a, okay, in a semiconductor material. The gap is always present. That means not easily this electron, right, this vehicle, the car is external electrons, and then that car is moving or is going to that road is nothing but the conduction, right? The actual current flowing to the another road, right? Suppose this vehicle going to that way, that second road, so we call as a free electrons, and that electrons is always for the conduction. So very important to be number of electrons present in valence band as compared to conduction band. So the conductor, you just see why the conductor is good electricity, because of the number of free electrons. This red color is nothing but the electrons, right? There are number of free electrons available in a conductor because of the valence band and conduction band both are overlap. There is no any gap present between conduction band and valence band. Now then the number of free electrons are available already in a the conduction band. So next example is copper. You know that copper and aluminum, the good conductor of electricity, and now is used in electricity, carries from one place to the another place. The conductor, the electrons can move freely among these orbital within an energy band as long as the orbital are not completely occupied. This is very important. So this is general diagram. The green color, so we call as a, right, the green color we call as electrons, right? Is a bunch of electrons present in a valence band, but there is no any electrons present in a conduction band. The gap present between the conduction band and valence band. The conductor, the valence band is empty, right? The valence band is empty in a conductors. So this is actual the conductor. So there are number of okay cars in a actual conduction band. The valence band, okay, valence band and conduction both the bands have the number of electrons. So conductor, they overlap the conduction band and the valence band. That's why the free electrons are already available. No need to increase that availability of free electrons in a conduction band. So also in conductors, the energy gap is not non-existing or relatively small. The insulator, you know that insulator, the valence band, there are number of electrons present in valence band, and now then the energy gap is very larger, and then there is no any electrons present in conduction band. Suppose if you jump the electrons, at that time you apply the very large voltage across the time. For example, wood, right? The wood, diamond, they not conduct the current because of the very small value present or electrons present in a actual material, right? So now you know that the insulator does not flow any type of current because of very large band present between valence band and conduction band. The insulator, the valence band is full, right? So now you know that there is no any other vehicle, right? The vehicle not enter to the other. This is the valence band, the okay actual valence band electrons available, and now there is no any possibility to okay not the another road available near to the actual this road, right? So it's a one-way road. In short, the one-way road available in a the actual the actual insulator material, right? Insulator is a good the acts as an escape proof. There is no any current flowing to that device, right? The conduction band and valence band are separated by the energy gap, and very large gap is in between the valence band and conduction band. Insulator, the energy gap is relatively large. So semiconductor, you know that semiconductor, the green color dots we call as the electrons, and this electrons is moving from the valence band to conduction band, and then empty the circle available in a valence band. This empty is nothing but the hole. You know that suppose this band is break, right? This bond is break. After that, the vacancy is available in that area, and that vacancy called as the positive terminal. That means holes. And then the jumping from valence band to conduction band is nothing but the process of the semiconductor material with the help of the external energy. So this is the actual operation. So now then after applying the voltage, that means we just take the some the area to just cross the road, and that is nothing but the energy. The energy is allowed to move from valence band to conduction band, and it is possible for the external energy. So external energy apply, then automatically road will be open, and now then the vehicle crossing their road from valence band to conduction band, and now then they are easy to move in the area. That area is required for the actual device. Semiconductor, the only a small leaf is required for the electrons to enter the conduction band. So this is the band gap energy. So metal overlap, then semiconductor, the low gap, energy gap in between the valence band and conduction band, and now very large gap in between conduction band and valence band is called the insulator. So this is about the basic the difference between all the material, that is that material used in a number of devices. For example, semiconductor is a basic building block of all the devices fabricated by using the semiconductor. The copper wire is all made up of the pure conductor, and now then the insulator is actually the proof, right? So here is a shock proof equipment, all the equipment made up of the insulator material, right? So you know that plastic is one of the best example, wood is one of the best example of this insulator. So silicon, you know that here the carbon silicon, right? Carbon silicon and germanium. So outermost shell have the 4 electrons, right? The 4 electrons valence band, and now this is nothing but the actual semiconductor material, right? So carbon is really used because of only 4 electrons moving around this, but not okay use in that, because the carbon, okay, carbon not break their bond, okay, it required very large energy for their operation. Silicon is a very useful semiconductor because of the outermost cell is 4, and then the is also one more cell is in between the outermost cell and the nucleus cell, right? So silicon, the crystal, how this the crystal form. So now then there are number of silicon atoms sharing their 4 electrons with a neighboring sharing 4 electrons and form the bond. That bond is nothing but the covalent bond, and now then this is nothing but the structure of silicon crystal, crystalline structure sharing the electrons. So this is the arrangement of silicon. So now here the inside that the nucleus, and then outermost cell we call as a the 2, then 8, and then 4, right? So total 14 the atomic number of silicon, and now moving around this, the yellow color we call as a electrons moving around the nucleus. So this is the covalent bond, already told you the bond okay, sharing the electrons, then the bond form, that bond is called as the covalent bond. Covalent bond is always present in a crystal. So now then this circle is nothing but the silicon atom, right? So total okay, there are million of silicon atom forming the covalent bond, and now then form the crystal, and this crystal material is in solid form, not in liquid or not in other form, is solid form because of crystalline structure of silicon is based on the material. So this is intrinsic silicon. Okay, you know that only silicon atom sharing the bond, sharing the electrons with a neighboring silicon atom and forming the crystal, that called the intrinsic silicon. That means there is no any other atom, there is no any other the material used in that, right? So now then silicon material, only the silicon, the semiconductor material used in the construction, right? So silicon crystal is different from an insulator, right? So this is nothing but the actual process. So you know that the movement of the electrons, okay, moving from this way, right? So now then the bond not break, and then the electrons coming from this side, left side to right side in this way. At any temperature above the absolute zero, the temperature, there is a finite probability that the electrons in the lattice will be knocked loose from its position. This is very important. So electron easily move in a particular, okay, area, right? So electron is capable to move from one place to another because of the probability is present in a, okay, material, and now that material can be moved in anywhere, right? This is intrinsic silicon structure. So then the whole you know that the breaking the covalent bond, then this circle is empty or vacancy available here, and then vacancy we call it the hole, and this dot, that is darkened portion dot, we call it the free electrons, because it moving from one place to the another place. The electrons in the lattice knocked loose from its position leaves behind an electrons deficiency called as the hole. This is very important. I already told that. Suppose the bond breaks, at that time the vacancy available in the same position, and that same position or that same location we call as the hole. And now then the dot is nothing but the electrons available in a anywhere, right? Is not in the same area. So already the crystal not break, but now then this dot is moving in any direction. There is no any problems. So the current flow through the device, the electron, this dots, okay, the increase the dot by using the external energy. So then availability of these dots are more, then the more current flow to the device. But you know that this dot, the available due to applying the external energy and then break their bond and now then form the actual crystal. So current is totally depends, or current flowing is totally depends upon the energy applied to the one point with respect to another point. This is intrinsic semiconductor because of all the silicon atom present in a material, right? All the silicon, there is no any other atom present in a crystal. So now then the holes moving from the positive to negative side, this is very very important. The holes going to the right side and the electrons going to the left side. Why? Because the electrons are the negatively charged particle moving toward the positive terminal of the battery, and the holes are the positive charge particle moving toward the negative charge of the battery. This is very high voltage potential, but now then you know that the silicon is a only material that required very small external voltage, maybe 2 volt to 10 volt or maybe 20 volt, not more than 24 volt required for the all the silicon atom as an extrinsic semiconductor. So major drawback of the silicon intrinsic semiconductor is to be it required very high voltage for their operation to break their bond and free for movement. And the second very important is to be the very large temperature range is also required, right? So that type of problem, that means availability of the free electrons are very less as compared to extrinsic semiconductor. So these electrons available by applying the external energy. But in intrinsic semiconductor, sorry, extrinsic semiconductor, so we add the impurity. So you know that there are number of impurity present. Okay, there are three to four color present on the screen. So now this color indicate that there are number of atoms present in a one pack, right? So you know that the silicon combined with boron or silicon combined with pentavalent and form the material, and that material after forming the after combining this impurity, we will just note down the actual electron present in a conduction band will be increases, right? So how this electrons increases? You just add the impurity in a pure semiconductor. So this process is called the doping process. You know that only one dot the color is changed as compared to remaining color, right? So all these red color dots are called as a silicon atom, and then only this yellow color we call as a boron atom or something pentavalent atom, right? Trivalent atom or pentavalent atom. And as we know that as per the atomic number of that atom, then the number of available electrons available in a conduction band. So doping process is very important. For example, what is doping? Doping is adding an impurity, right, with a pure semiconductor. So this type of impurity depends upon the element added, right? So now then which type of element or which type of material you will form. Suppose if you want to make the n-type semiconductor, at that time you take the pentavalent impurity, right? And the p-type material, sorry, trivalent impurity added with the silicon, we call as a n-type material, right? So now here the p-type doping, these are okay, these two are the common atom added with the silicon atom. So boron and gallium, right? Trivalent impurity, the total the outermost cell electrons are 3, outermost cell electrons are 3, we call it the pentavalent doping. So p-type doping, boron or gallium is the dopant, right? So is the dopant. So this is very simple structure of p-type doping. So now as we know that the boron, okay, have the only 5, right? So only 3 electrons outermost shell, and now then it accept the 1 electron from the neighboring atom, and now then the vacancy is available. This vacancy is nothing but the hole. You know that major charge particles are the hole, and this hole formed by the boron atom, right? Formed by the boron atom, because the available electrons, you know that, okay, the 4 electrons, and now then the boron is nothing but the actual the pentavalent, sorry, trivalent impurity, and you know that the 3 electrons combined together. One more requirement, so 2 is here, 2 is here, right? 4, then 2 is here, and then 1 only, right? 2 to 4, and then 2 6, and one more, right? So now each and every atom share with the boron atom. So boron and gallium each have only 3 outer electrons, and the sharing with the neighboring atom. And now one more vacancy is required. That vacancy we call the acceptor impurity create a hole. So now accept the 1 electrons, and now then form the bond, and that bond called as the pentavalent, sorry, the acceptor impurity we call as the hole, and the p-type material will be formed. When mixed into the silicon lattice, they form the holes in the lattice where the silicon electrons has nothing to bond to. So this is very simple. The diagram, the conduction and valence band, the extra hole, energy level, the Fermi level. Now you know that the electrons present in a hole, the valence electrons is coming from the valence band. So the absence of electrons create the effect of an positive charge, hence the name p-type, right? So now then the p-type, in short, the p-type accept the electrons because of trivalent impurity added in a pure semiconductor, and now then the total 3 valence electrons present in the outermost shell. So one more required, because the silicon atoms have the 4 electrons, and these electrons accepting from the neighboring atom and form the vacancy. That vacancy is called the hole. That's why the in p-type doping, in p-type material, the majority charge carriers are the holes, and minority charge particles are the electrons. The holes can conduct the current. A hole happily accept an electrons from the neighbor, moving the hole over the space. The p-type silicon is a good conductor, right? So now then p-type silicon formed by the acceptor trivalent impurity, and now then silicon atom, and this is called the acceptor atom, right? So now then the n-type. So n-type material always take the pentavalent impurity. That means outermost shell electrons are 5, right? So 5 electrons present in outermost shell of phosphorus and arsenic. So n-type doping, the phosphorus and arsenic is added to the silicon in a small quantity. So now then this is very important. So total 4 valence electrons of this Si, then 4 valence electrons of this Si, then 4 of this Si, and 4 of this Si. This is the structural representation of n-type semiconductor material. So what this dot why left from this position? Because of the total electrons present in the outermost shell of this SB is 5, right? 5. So only 4 required. So one share with this electron, this Si. Second is here, third is here, and fourth is here, right? The 4 electrons share with this 4 Si atom, one more remaining, and that electrons left from the position, and that is called the donor impurity. So n-type material electrons are always called the donor impurity. Donor impurity means it donates the electrons, and now the number of electrons available in a conduction band, and this is very important. N-type material, major charge particles are the electrons, and minor charge particles are the holes. So phosphorus and arsenic are the best example or best impurity added with the pure semiconductor Si. So this is the diagram. Then extra electron, the conduction electrons. You know that there is no any valence hole present in a valence band, but the electrons present in a conduction band. Extra electrons energy level available, already available in a conduction band due to the addition of the impurity in a pure semiconductor. So this is the basic difference between the n-type and p-type semiconductor. Silicon is doped with an element having a valence of 3 electrons. That means trivalent impurity. Silicon is doped with the element having the valence of 5 electrons. that means pentavalent impurity. To increase the concentration of hole, this is very important, to increase the concentration of electrons n and p, right? Small n and small p, because hole is always denoted by p and the electrons are always denoted by n. One example is boron, the trivalent impurity boron, then the pentavalent impurity phosphorus or arsenic. So doped the p-type semiconductor, n-type semiconductor, you know that this is the structural diagram of the n-type and p-type. The 3 plus 3 and here's all 4, right? Plus 4. Now then it accept the electrons from the neighboring atom and from the actual p-type material. Here donate the atom because of 5 plus 5 band. So here the carrier transformation, then very important is to be carrier transport. There is no any formula in intrinsic and extrinsic semiconductor, but now very important to be this material. Okay, there are number of procedure in a material. That means after applying the voltage, what will be the parameter will form, right? The parameter already noted in a first line. The carrier transport, that is carrier. You know that the motion of carrier, right? How to move the carriers, that means electrons and holes. Only two carrier present in a material. दोनच carrier आहेत material मध्ये, ते म्हणजे electrons आणि hole. So as per the polarity applied across the material, then the movement, okay, will be formed, right? So now in semiconductor the leads to be current. Now then very important, the move the atom charge particle, then current start flowing, right? So current कसा फ्लो होतो, तर ज्यावेळेस मुवमेंट होईल चार्ज कार्याचं त्यावेळेस करंट स्टार्ट होतो. So movement, but you know that the resistance is always important. The current and voltage and resistor are always related to each other. So voltage is always directly proportional to the resistor because constant value, and current is always changeable. And the current and resistor always inversely proportional. This is very important. The current, okay, there are two current flowing through the device: diffusion current and drift current. Only two current present in a material. Suppose once you switch on the power supply. Once you switch on the power supply, at that time the two current flowing through the device, that current, okay, are the diffusion current and drift current. So now then the electrical field, you know that electrical field is always mentioned in the actual operation or in actual analysis because of voltage, right? Electrical field is always denoted by voltage V, capital V. Due to an externally applied voltage, since the carrier are charged particle, right? Both the carriers are charged particle. That means negative charge particles are electrons and positive charge particles are the holes. And we will refer the transport mechanism as a carrier drift. So diffusion current, what is the definition of diffusion current? The carrier diffusion is due to the thermal energy which cause the carrier to move at a random even when no field is applied. That is very important. So diffusion process is nothing but the concentration of charge carrier. Concentration of charge carrier. You know that suppose if we combine the opposite charge particle, what will happen? The concentration will be formed, right? Concentration. Or then force of attraction. You know that force of attraction and force of repulsion. Same charge particle always repel, but the opposite charge particle always attract. You know that. The diffusion is a process is totally depends upon the force of attraction in the same device without any energy applied across it. तुम्ही एनर्जी कुठलीच अप्लाय करायची नाही आणि त्या मटेरियल मध्ये जे चार्ज कॅरियर आहे त्यामधनं जे मुवमेंट होतं त्याला म्हणतात आपण डिफ्युजन करंट. सो डिफ्युजन करंट इज always depends only on the concentration of charge carrier because of you combine the opposite charge particle and always attracted to each other and move their position or moving from one place to the another place because of force of attractions, right? So this is very important. And the drift is nothing but you apply the external energy and that we will form the movement. हे खूप महत्वाचं आहे. So now the diffusion current and drift current, thermal energy, that means thermal energy is nothing but the internal energy, and now the external energy we call the electrical field. So you apply the external voltage and you form the current, you form the movement, and that movement called the drift current. So drift is nothing but the changing the position from one place to the another, or we some apply the some force to the next charge particle, right? So one place to the another place, then the drift. And then suppose is there an obstacle present in between your way, right? At that time we take the drift, right? We just change our route, and now we will move toward the actual destination, right? So this is called as a drift current, the charge particle motion in response to an applied electrical field. When an electrical field is applied across the semiconductor, the carrier start moving, producing the current. This is very very important concept. So mobility is also right. The third parameter is mobility. Mobility denoted by small u. You know the small u, right? Mobility is a very important parameter. Suppose if you analyze the actual semiconductor material. So mobility in a solid state physics, the electron mobility, we call it the electron mobility. The characteristics, how quickly an electrons can move through a metal or semiconductor. This is very very important. So mobility, you know that mobile is just portable device, is always move from one place to the another place. How this device move from one place to the another, that concept called the mobile device. Similarly, the mobility, that means nothing but the electrons. How electrons move from how these electrons quickly move from one place to the another place, we call it the mobility. And this mobility denoted by mu. And then there are two concepts in that: the pulled, right? Pulled, you know that push, right? So pulled by an electrical field, or there is an analogous quantity for holes called as a called hole mobility. You know that there are two mobility in a device because of due to two charge particle: electron mobility mu n, small n, and the whole mobility we call as a mu p. And there are two charge particles in that device. That's why there are two mobility, mu n and mu p. And always exam asks you just take the mobility of electrons and you calculate the density or then resistivity or conductivity of that device. So resistivity, the semiconductor have the bulk resistivity in the range of 10 raised to minus 4 ohm cm, heavily doped, to 10 raised to 3 ohm, that means 1k in short. Intrinsic, that 7 of the magnitude semiconductor element include the silicon and germanium. It is no coincidence they are both from group 4 of the periodic table. So this is very important. Resistivity is, you know that, denoted by R, and you know that the formula for resistor is equal to rho L by A. So length of the conductor and the area of the conductor and the resistivity of that material. And the resistivity always mentioned in a data sheet. Okay, already mentioned here. The resistivity of semiconductor is from 10 is to minus 4 ohm to 10 is to 3 ohm. All the equipment, right? All the devices, resistance always in between that range. Okay, now then the component, okay, made up of, you know that the material p type and n type. So passive and active component, you already know that passive component does not require any type of power supply. So now it conduct the current without any power supply. The examples are resistor, capacitor and inductor. The active components, okay, do require the power supply for its operation. Or the device which electrically connects depends on the power supply. The transistor such as BJT, FET, all type of ICs, all are the active components. So this is for your knowledge point of view, just I have added. So now let's start the drip current. How will calculate the drip current? So what happened, this is very important line, what happened when the electrical field E is applied to the semiconductor crystal? आपण जर इलेक्ट्रिकल फील्ड जर त्या क्रिस्टलला अप्लाय केली तर काय होईल? So now then first point, hole are accelerate in the direction of E, right? Free electrons are always repel, right? So free electrons are repel and the holes are attracted. Why? Because positive potential and negative potential, and now the holes always attracted toward the negative potential, and the electrons always repel from the negative side, right? How is the velocity of the hole defined? So velocity of the hole, so Vp drift is equal to mu p multiplied by E. Mu p means hole mobility and E means electrical field. So V, this is very important formula you keep in mind. So velocity of light or velocity of these electrons, you know that velocity of light 10 to 10 raised to minus 8 meter per second. Similarly, the velocity of hole is equal to mu p multiplied by capital E, electrical field. Or then similarly the same formula for N type, right? So electron mobility is equal to the velocity for N or electrons defined as a minus of mu n multiplied by E. Why minus? Because of negative charge particles. So this is very important formula. So then note that the electron move with velocity 2.5 times higher than the holes. This is very very important. So now then the velocity of electrons is always higher than the hole. That's why we always prefer the N type material, right? We always the conduct the current by using the electrons, by referring the electrons, right? So electrons is a major part of your all the electronics device. The electrons maximum, then it conduct the current very large with a very less time, right? So delay, you know that the time is very important nowadays. The time factor is totally depends upon the which material used in that. Suppose your the electrons constitute the current, then it is better for your application. But the conduct the current using the holes, then the very less time or the more time is required to form the applications. So this is very important formula for your understanding purpose. So electrical field denoted by or represented by hole per centimeter, right? Hole per centimeter, right? Then mu p centimeter square per Vs, that is equal to 480 for silicon. This is very important. 480 for silicon mu p, and mu n mobility of electrons, mobility of holes, centimeter square per holes. Then 130 1350 for silicon. So Vp is equal to mu p Ep. This is same formula to calculate the velocity of hole and velocity of electrons. This is very important diagram. So now then, suppose if you apply the external voltage to one point with respect to second, so then the electrical field going to the going to the right side. Why? Because the positive to negative, the electrical field hole per centimeter, right? You know that the electrical field going to this way. So shifting from left side to right side, and the same direction the holes are going, right? All holes are going in a same direction because of positive. But the electrons are always repel. The electrons always repel, and now then it is attracted toward the positive terminal. The electron. This is always, you all know that the silicon cause the holes to drip in a direction of electrons, right? And then the free electrons to drip in opposite direction. Both the holes and electrons drip the current and are in a direction of electrical field. Drip current once again. They assume that for the single crystal silicon bar on previous slide, the concentration of hole is defined as P and electrons as N. Concentration of hole, already told that. What is the current component attribute to flow of holes, not electrons? This is very important. Consider the plane perpendicular to x direction, right? So now then, perpendicular to x, define the whole charge that cross this plane, and you know that the formula for IP, the current flowing to the device due to flowing of holes, is equal to AQP VP, right? AQP VP. What is A? Cross sectional area of silicon. What is Q? Magnitude of electron charge, that means charge is just, you know that charge, and P is nothing but the concentration of hole. And now then Vp, the concentration of charge is always mentioned in data sheet. Q is also mentioned and A is also mentioned. You only calculate the Vp. What is formula for Vp? Mu P multiplied by E. Mu P multiplied by E. So then substitute the mu P in E. So what is the, okay, our target is to be JP. What is junction, right? You know that the actual, the component, the JP is equal to IP divided by A. The current density, you know that current density is also important for your the gate point of view. You just calculate the current density by taking the mobility of holes or mobility of electrons, cross sectional area, then charge of the electrons, charge of the holes. So formula for current density is equal to JP is equal to IP divided by A. And what is JP right now? Q multiplied by P multiply by mu P multiply by E. Then A cancel. Why A cancel? Because previous, you just see the previous formula. Here A, right? IP is nothing but the A QP QP VP. Now then this is cancelled, and now your final formula for current density is equal to QP mu P E. You keep in mind this formula and always record for the solving the problem. What is the current component attribute to the flow of electrons? Similarly, we calculate the current density in combination of JP and JN, right? The overall current density of the device, of the actual the diode or something, for example transistor. So JP plus JN, the Q is common for both these, charge is common. And now you know that this factor is nothing but the conductivity. This is very important. Conductivity is also one more topic in your syllabus. Only 3 formulas are required. What is first formula? Velocity, right? We came from the velocity, right now velocity mu p vp or vn minus un e. Second formula ip, right, in terms of the charge, in terms of the cross section area, and in terms of the concentration of hole, by putting the vp, and this jp is nothing but the ip by a, and then jp is equal to this formula. And you know that the conductivity of this material is equal to the addition of current density of hole and current density of electrons is equal to q p mu p plus n mu n multiply by e, right, multiply by e. And this is a very simple formula. The electrical field always given, so you easily calculate the electrical field by taking the voltage and the taking the area and actual voltage. So this is the very important concept for your exam point of view. Only you keep in mind this all the formulae, and now then always required to solve the 2 marks problem, right? So now maybe ask in incoming exam, they conduct you, just find out the conductivity by taking all the ratio, right? The conductivity is related to the current density and electrical field. So what is the Ohm's law? Says that J, current density, is equal to conductivity multiplied by E. Conductivity multiplied by E. Just you see here, the conductivity formula is equal to Q in bracket P mu P. P is nothing but the what is charge carrier, right? So concentration of hole and concentration of electrons. Here the concentration of free electrons and concentration of charge. You know that this conductivity multiplied by electrical field is nothing but the current density. And you know that the formula for the conductivity is equal to Q in bracket this, right? And the resistivity is the reciprocal of conductivity. Resistivity is the reciprocal of conductivity is equal to the J is equal to E divided by this sigma, and now the sigma is equal to 1 upon Q P mu P plus, right? You take the reciprocal of this 1 divided by the sigma, we will get the actual resistivity, right? So conductivity and the resistivity both are the important for your exam point of view. So based on that, you just solve the problems. So here find the resistivity of intrinsic semiconductor using the following value, the mu n given. So what type of problems given in examination, you just look into the actual picture. So always you keep in mind this. I will share the same PPT in your WhatsApp group, so don't worry, don't note down this value. So mu n is given, mu p is given, ni is given, and now then you calculate, find out the actual resistivity, right? So E is given. So then find out the resistivity of P silicon, Na given, then using the mu n, and now then all the values are given. So you just calculate with the help of the diagram. For intrinsic semiconductor, the number of free electrons is Ni and number of holes is Pi. Very important to be how we will count the number of electrons and number of holes in a material. आपण कसं ठरवणार की त्याच्यामध्ये किती इलेक्ट्रॉन्स आहेत आणि किती होल्स आहेत त्या मटेरियल मध्ये, तर ते दोन डिनोट करण्यासाठी Ni and Pi, right? So this numbers denoted by Ni for free electrons and Pi for 4 P holes. So P type doped semiconductor always denoted by Np and Pp. बघा याच्यामध्ये नोटेशन बघा, नंबर ऑफ फ्री इलेक्ट्रॉन्स होल्स Pi and Ni, नंबर ऑफ डोप्ड रिजन म्हणजे डोपिंग म्हणजे इम्प्युरिटी किती आहे त्याच्यामध्ये कोण ठरवणार, Np and Pp. And then for N type doped region, so we just denote by Nn and Pn. So what are the P and N? So P and N are nothing but the doped region. So actual the free electrons and holes denoted by the P and N. P means P means holes and the N means free electrons. So carrier diffusion is the flow of charge carrier from area of high concentration to low concentration. Carrier diffusion, there are 2 types of diffusion, carrier diffusion and diffusion current. So you know that diffusion current. So carrier diffusion is nothing but the charge carrier moving from high concentration to low concentration. It requires non-uniform distribution of carriers. Non-uniform distribution means not equally distributed. So now then one particular area have the some number, a greater number, but some of the area, for example in classroom. So now the number of students sitting in a back side, right, and only 2 to 3 students the sitting in a first benches. So that is called the non-uniform distribution. But suppose you distribute two of each of the bench, you call it the uniform distribution. So non-uniform distribution always required for the carrier diffusion. And now you know that diffusion current is totally depends upon the charge movement and the current flow that result from diffusion, right? Diffusion is nothing but the movement of the charge carrier due to of the concentration from low to high or high to low. This is the diffusion current. So now there are three concepts: the whole injection. Now here the injection hole, then concentration profile arise and diffusion occurs. There are three concepts in a current: inject the hole. Then second, inject means you know that externally the injection in short, okay, in medical field, injection, right? So you extra take the dose with the help of the needle, right? You know that needle, or you can tell that the injection, right? Injection. So injection is nothing but externally supply the some energy into your body. Similarly here, you inject the hole. That means you just supply the holes into that body. You just add the number of pulse प्लस साइन इंटू युअर डिव्हाइस. तुम्ही त्या डिव्हाइस मध्ये प्लस साइन वाढवायचे, त्याला म्हणायचं इंजेक्ट होल. सो प्रोसेस टू इन्क्रीज दी नंबर ऑफ होल्स इन युअर the material externally. Concentration profile arise, that means the continuous hole inject and then concentration profile arise, right? So you can continuously inject the hole at one particular point, then the all the holes, right? So now then the holes equality present in your device. The diffusion occurs because of concentration gradient. Hole will flow from left to right. So now then hole always flowing from left to right and electrons always moving from right to left in general the description. And this graph shows that the whole concentration P and X direction. So as we know that at this point the left side the very large okay value of P, but now we assume that we just cover the distance. Suppose we cover the distance at this last end, at that time the availability of whole concentration is very negligible, because of we reach the destination. So diffusion current definition, though this is very important definition. Diffusion current defined as Jp current flow density attributes of hole, Q magnitude of electrons charge, dP diffusion constant hole concentration point, and dP by dx gradient of holes. Hole diffusion current density Jp is equal to, this is the very important formula for your exam point of view. You keep in mind only 4 to 5 formulae present in this topic, and you keep in mind and you usually solve the 2 mark or 4 marks exam problems in your regular examination, right? GATE examination. So now Jp is a whole diffusion current density. Diffusion current density is equal to Q charge particle multiplied by dP. dP is nothing but the diffusion constant of hole. And I always mention data set here. dP is value 12 centimeter square per second, and this parameter always cancel to each other. So dpx divided by dp. Px is nothing but the whole concentration at point Q. At point Q, at middle, at left side, at right side. We just take the distance of that, and we take the derivatives of that, change of distance with respect to time, right? You know that Q dp, the constant parameter multiplied by change of the whole concentration from one place to the another place, dp by dx, dp by dx gradient of whole concentration. And then dn is also 35 centimeter. So only one negative sign present in both the equation because of the electrons, right, moving from one place to the another place, from right to left. Consider a bar of silicon in which the whole concentration Px described below in a established. Find the whole current density Jp at x0, right? x0 ला किती असेल Jp to find out करायचं. Find current Ip. So now then what is the formula for that? Following parameter: Po is equal to 10 raised to 16 centimeter, Lp is equal to 1 micrometer, and A is equal to 100 micrometer. So the formula for that, so Px formula, that means what is Px is nothing but the whole concentration at point X, and the formula for that is nothing but the Po is equal to Po multiplied by e raised to minus x divided by LP. LP is given, the X is given, right? And now you know that the PO is also given. So with the help of this formula, you calculate the PX value and you note down that value in your formula. And now just calculate the actual the diffusion current density in your problem, right? So this is the relationship between D and mu. So what is D? Right, D and mu is a mobility and D is nothing but a diffusion constant. Mobility आणि diffusion constant मध्ये काय difference आहे? It's a very very important formula, and always what is this value? T is always 300 Kelvin and VT is always equal to 25.9 millivolt. तर VT ची व्हॅल्यू नेहमी एवढीच असते. VT ची व्हॅल्यू is equal to the ratio of these two factors. So this ratio is always keep in mind. The constant, diffusion constant divided by mobility is equal to diffusion constant of the whole divided by mobility is equal to Vt, and this is known as the Einstein relation. So Einstein always tell that you take the ratio of these two, you will get the temperature is equal to 25.9 millivolt, right? Millivolt, sorry. So then drip current density, diffusion current density already over. Then what is formula for that? You just keep in mind the formula Jp, right? So Jp stands for diffusion P and diffusion N. And here the drip current density is always formed by electrical field. So E is involved in that. Diffusion current, don't consider E because E is absent. But here the drip current is always calculated by taking the E, right? E is nothing but the electrical field. So concentration gradient in free electrons and holes. So this is very important formula for drip current. J drip is equal to J P drip plus J N drip. Similarly, Q P mu P plus N mu N E. And the formula for that, so after you put just value the Q, then dP multiplied by dpx by dx minus of q dn dnx divided by dx, and this is very very important formula, and you easily solve the problem with the help of this formula. Only one changes to be, you just take the individual the ratio and now then subtracting from each other, you will get the diffusion current density. So generation and recombination of carrier, you know that whole electron hole pair generation, right? This is very important concept. Electron hole pair generate कसा होतो, right? So carrier मध्ये electron hole pair एकत्र येतात आणि त्याच्यामधनं काय होतं, constitute current, right? So we know that we just move from one place to another place by combining the electrons and hole pair in that area, right? आपण कसं करतो, इलेक्ट्रॉन आणि होल एकत्र येऊन त्यामध्ये काय होतं, शिफ्टिंग विल बी स्टार्ट. So carrier generation describe the processes by which the electron gain energy and move from valence band to conduction band, producing two more mobile carriers, while recombination describe the process by which a conduction band electrons loses energy and reoccupies the energy state of an electron hole in the valence band. That is very very important concept. रिकॉम्बिनेशन डिस्क्राईब काय करतं, तर कंडक्शन बँड मध्ये इलेक्ट्रॉन जे लूज एनर्जी करतात त्याच्यातनं ते ऑक्युपाय होते आणि ते एनर्जी काय करतात, व्हॅलन्स बँड मध्ये ऍडिशन होते. सो नाव यू नो दॅट द मुवमेंट इज व्हेरी इम्पॉर्टंट अँड दिस मुवमेंट इज ड्यू टू द एक्सटर्नल एनर्जी. द रिकॉम्बिनेशन ऑलवेज टेक प्लेस इन अ डिव्हाइस. सपोज the electron present in an n-type material crossing the junction and recombine with the holes in a p-type material. The recombination take place in a p-type material, and similarly the holes recombine with electrons in an n-type material, and this recombination constitutes some energy, and that energy is in the form of light or in the form of something, and that is used by the LED, right? LED is always emit the light because of recombination take place and some release the energy in the form of light. But now here the recombination take place, and now then the after recombine the electrons, then they construct the current into that device. So this is very important, the flow chart of generation and recombination of carrier recombine कसं होतं आणि ते generate कसे होतात. So carrier recombination, this is very very important, the diagram. Electron present in a conduction band and the holes present in a valence band. बघा, इलेक्ट्रॉन आणि कंडक्शन बँड. So now then, suppose your electron after applying the energy, external energy, काय होतं मग electrons break always moving from conduction band to the valence band and then recombine take place. या दोघांमध्ये काय होतं, ह्या रेड मध्ये आणि ह्या येलो मध्ये रिकम्बिनेशन टेक प्लेस होतं आणि त्या रिकम्बाईन होताना काय होतं, एनर्जी generate, right? It generate the energy and that energy is always okay, always going to this direction, right? You know that the energy is going to this direction. So here the electrons and holes recombine take place and the energy will be released. So here mean the lifetime of carrier. So lifetime of carriers is always in between that the generation and the generation, you know that generation recombination. ज्यावेळेस आपल्याला एनर्जी पाहिजे असेल त्यावेळेस काय करायचं, रिकम्बाईन करायचं. बघा एलईडी मध्ये डायोड मध्ये आपण रिकम्बाईन करणार आहे का, नाही, आपण जनरेट करणार आहे. सो इन एलईडी वी रिकम्बाईन दी इलेक्ट्रॉन्स होल पेअर इन अ बँड, राईट, इन अ कंडक्शन, इन अ फॉरबिडन गॅप. But here the generation is nothing but the moving the electrons from the valence band to conduction band, and then it takes some energy for that process, right? So for that process it required the energy and external energy is applied to that point, and now then combine take place. So here we release the energy from one place to the another place. This is called the carrier. And then carrier, two types of carrier, the recombination of carrier and generation of carrier. So there are two important diagram that shows that the actual process. So generation, recombination and injection are the three procedure, sorry, always required, and their formulas is also required for the solving the problem. The electron hole generation, the thermal excitation of electrons from the valence band into the conduction band. बघा व्हॅलन्स बँड मधून कंडक्शन बँड मध्ये गेला तर त्याला काय म्हणतात, इलेक्ट्रॉन होल पेअर जनरेशन. And recombine means there are two concepts, generation and recombination. Recombination कधी होणार आहे, so radiative recombination, that means photons, non-radiative recombination, lattice vibration and photons, the Eiger process, you know that generation and recombination. So generation is always from valence band to conduction band, you always take care, okay, they always keep in mind. जनरेशन कसं होतं, द व्हॅलन्स बँड मधून कंडक्शन मध्ये इलेक्ट्रॉन गेला तर त्याला म्हणतात जनरेशन, आणि त्याच्या अपोजिट द रिकॉम्बिनेशन इज फ्रॉम conduction band to valence band, conduction band to valence band, we call the recombination. And now EC and EV. So for that purpose we require the important formula. So here the GO is equal to RNOPO, recombination coefficient R, centimeter per square is always given, but now NO and PO we will calculate with the help of the formula. So GO plus R, RNP, the R injector, and now then the tau is nothing but the actual electron hole pair recombined lifetime. So 1 upon R is nothing but the recombination coefficient, in bracket the addition of both the charged particles. So generation and recombination of carriers are of 7 types. बघा ते carriers recombination आणि generation किती types आहेत, total 7 types. So out of that the band to band recombination, trap assistant recombination and Eiger recombination we will take. Simple recombination, generative model, band to band recombination, tap assistant recombination, then surface recombination, Eiger recombination, and general due to light. So here one electron combined with one hole we call it the band to band. Then here the changing the energy, right, tap assistant, now changing the electrons from one place to the another place. So these electrons and this hole not recombine, these electrons recombine with the other electrons, right? So now here the one electron moving to this direction and second electron moving to this direction, we call it the Eiger recombinations. So now then these are the important formulae. So now you keep in mind there is no any other explanation. So now you take care of that. So always you keep in mind. But now some of the formulas, this is very important Fermi level. So always represent the carrier generation. So this is also formula. The previous slide don't take care of this formula because really asking the problem based on the recombination equation. But here the Fermi level, okay, widely asked in or most of the time asked in examination. At equilibrium, semiconductor experiences their generation of EHP at the rate GTGI, which is balanced by the recombination rate, so that equilibrium concentration of NO and PO are maintained. So this is very important. So how to maintain the equilibrium condition? That means initial condition. All the charge particle movement, then critical problem. But all the charge particle present at constant or stability. In short, all the electrons are the stable. So then you apply the energy, then all the electrons start their conduction, right? All the electrons or all the holes moving from one place to the another place. But now in general, all the electrons and holes are always steady, right? Always equilibrium condition. So this is calculated by gt is equal to alpha r ni square. So alpha r no po is nothing but the carrier concentration of electrons, free electrons and characteristic of hole, and alpha is a constant parameter. So alpha is nothing but the constant parameter and always mentioned in a data set or always given in a data set. So if the steady light is shown on the sample on the optical generation rate GOP will be. So this is so another part. So now we just add the equilibrium condition deviation from the equilibrium, the delta n and delta p also added with the NO and NP. We separately calculate by adding this factor. But the general formula, the gap, suppose the optical generation, that means light concept not involved in that. At that time, this is standard formula. But suppose light is involved in that, what will happen? The NO plus delta n and PO plus multiply by PO plus DP will be involved in that. Poisson's equation, so they are used to solve for the electrical performance of the electron device upon applying the stimulus on them. The stimuli is in the form of voltage or photon or thermal energy. The Poisson equation is always required to represent the electrical performance of that device. This means by using this equation, we can calculate the electrical performance of the device and the derive IV relation for them. Upon mathematically, so we will calculate the relationship between current and voltage with the help of this equation. So Poisson's equation correlate the electrostatic potential psi to given charge distribution, then the rho, right? So this is very important. The Poisson equations based on the Gauss's law. The Gauss's law is also used to Poisson equation. So most of the Maxwell equation is required to represent the Poisson equation. Now the Poisson equation is used to obtain the quantitative solution for the electrostatic variable. The charge density is always denoted by rho, right? So you know that this is rho. Then the permeability, the permittivity, and the charge density is also important. So you keep in mind only this formula. So d permeability epsilon divided by dx is equal to rho by es. And what is the you know that this is nothing but charge density. Charge density divided by permittivity is nothing but the Poisson's equation. So Poisson's equation represent the relationship between voltage and current, right? Voltage and current. So dielectrical constant Es is a dielectric constant. ER is always equal to 11.9 for silicon, and now then epsilon O is equal to 8.854 multiplied by 10 to minus 14. So now then minus d square v by dx square is equal to rho es. This is the formula, the updated formula to calculate the actual charge density present in your the field, right? So this is the very important formula for that. So continuity equation, the continuity equation based on the conservation of mobile charge E and whole continuity equation are given by, so dn by dt, so change of the electrons with respect to time is equal to 1 upon charge particle. D current density divided with respect to distance minus of Rn recombination rate. Rn is nothing but the recombination rate of electrons plus Gn is a generation rate. The recombined rate plus generation rate is nothing but the continuity equation. The continuity equation is based on the conversation of mobile charge E and whole continuity equations are given by, right? So dp, this is dn, dp by dt exactly opposite minus of 1 upon q, d by jp divided by jx minus rp plus gp. So now only this formula is required for the calculated in the continuity equation, calculated in the how much change of the electrons with respect to time. So this is about the today's session. So the PN junction diode, then the BZT, then BZT and MOSFET, and the different types of other the topics we will discuss in the next session. So here, is there a doubt in present in your mind, you can ask. So I will give the one assignment. I will conduct the exam, online exam based on this PPT. So I will share the some PPT, and now then you just find out that find out the formula and try to solve it. I know that this is very difficult. This is very critical situation. So now how will solve that problem by using this formula? But you can just try to identify all the given parameters in an equation. So you know the given parameter, you already you know the parameter, you easily use the formula to solve that value, right? So this is very very simple way to uh, take the actual value. So now then here here there is any question present in your mind, you can ask me. Then I know that the very you know that the total 12 marks for that subject, and now you will get total 8 marks out of that 12 marks. So using only 5 to 6 formulae present in a the first topic, and now also then second and third topic, right? So now then we will meet again. We will meet again in a Mondays, right? In Monday, I think 11 12, right? So 12 October 2020. And now you just give the feedback to this. I will share the link of today's session. Just to wait. Attendance and feedback link. So if you please fill this link, and now then I will mark your attendance. Okay. Thank you for coming for this session, and I will share my notes to you in 5 to 10 days. So already I have all done the all the notes of EDC related to the gate exam, right? So thank you. All of you please fill the form, and you can leave now. Now then session is over.